Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. We are discussing about stereogeometry, and in the last lecture we discussed different geometric parameters of a stereo configuration and also the relationships between the corresponding points under a stereo setup. And there we have seen that there is a particular entity which is called fundamental matrix, which is associated with a stereo system, and this fundamental matrix establishes the relationships between the pair of corresponding points, and it has also many other information encoded within it. So, we would like to see the properties of this fundamental matrix. So, first we consider that the relationship between the corresponding point in the stereo setup. You see, this is the corresponding point because they are the image of the same scene point, and this can be expressed using a fundamental matrix which is of size 3 cross 3 size using these equations. That means x prime transpose fx equals 0 or x transpose f transpose x prime equals 0 for any pairs of correspondence point, which means if I consider another point, say y, and if I take its projection on the image plane, say this is the projected point in this image plane, and say this is the projected point in this image plane. So, for this point also it will satisfy y transpose f y prime transpose f y equals 0 or y transpose f transpose y prime equals 0. So, this is meaning of the interpretation of the fundamental matrix. The next thing is that if a fundamental matrix is defined for a camera pairs P and P prime, you see that with respect to this configuration, the camera defined by this projection matrix, so P or P prime are the projection matrices of this camera. So, this acts like a reference camera, and this is the other secondary camera of the stereo system, if we say as far as the coordinate convention goes. So, then for them the fundamental matrix, if it is defined F, because you can see that with respect to this reference image we consider this representation of x, and for the other camera we consider the x prime, and accordingly this equation has certain order of your sequence of these particular entities. So, when we reverse this role, then the fundamental matrix should be F transpose, because in that case in the reversal role this becomes the image point of the reference camera, and this becomes the image point of the second camera. So, for that the same relationships will reflect when F gets transposed. This is also true for the mathematical point of view. If I take the transpose of this expression, I will get this one. So, that is also equal to 0. So, because this is only a single linear equation. And from fundamental matrix you can get the epipolar lines which are passing through the epipoles, and epipolar line contains the corresponding point. So, for this let us consider this diagram once again. For this point, its corresponding point lies on a epipolar line which is passing through the epipole, and this epipolar line is given by the product of fundamental matrix and the point. Now, you should note that all are in the projective space or using the homogeneous coordinate system. And on the other hand, the same relationship also holds from the other point of view. That means if I consider now, this is the reference camera, so and this point has the corresponding point x. So its epipolar line L, where it lies, the corresponding point lies on the epipolar line, and which is given by F transpose x prime. You should note that also, that we have already expressed fundamental matrix as a product of two particular matrices. So F is E cross H, where H is a homography induced by a plane. So that also we discussed in the previous discussion, and both of them are 3 cross 3 matrix here. This one is giving E, actually this operation is E cross Hx, that is equal to L. E cross Hx will give you the L. So if there is a plane induced homography H, then this is E prime, it should be E prime. So E prime cross x prime, and x prime is Hx, that would give you L prime. And since x transpose, x prime transpose L prime equal to 0, as x prime is contained in L prime, so this will give you x prime transpose E prime cross Hx equal to 0. That is the equation, and this can be expressed in the composite form, in a matrix algebra form, this cross product that we have seen by a particular matrix which is E prime cross H. And E prime cross can be derived, this we discussed in the, say E prime, if it is a vector in the form of Ex, Ey, Ez, then we can derive this E prime as, it's a skew symmetric matrix, so diagonal elements are 0, and this one is minus Ez, this is Ey, this is minus Ex, and it is Ez, this is minus Ey, and this is Ex. So E prime cross is equal to this matrix. Equivalently, it is performing the corresponding cross product of vector E prime cross x prime or E prime cross Hx, both. It is equivalently performing. So these are certain things we discussed in the previous class, and we are continuing this discussion in this lecture also. So epipolar lines are given from the fundamental matrix, given the corresponding image point. So image point of one plane, image plane, will give the epipolar line of the other image plane simply by multiplying the fundamental matrix with that point, with that stereo configuration. And the roles can be reversed also. So there is a name, another generic name of this kind of matrix transformation. So it's a transformation. So we call this transformation is a correlation transformation, because the transformation of a point becomes a line. So in a homography, you see transformation of a point becomes a point, or transformation of a line becomes a line in the homography transformation. But whereas in this case, a point becomes a line. So we can understand that this kind of transformation can never be one-to-one transformation, because when I am transforming a point, I am getting a line. So the inverse is not possible. From the line, it is, I do not know that which point I should get. That is the problem. So there is, so the inversion is not feasible in this case, and that's why it is a rank deficient, or its inverse does not exist. So that is a property of this fundamental matrix. For the epipoles, we can see that the epipoles, in epipoles are also lying in the epipolar line, because that is what all the epipolar lines, they converge at epipole. So which means that E prime transpose L, which is again given by the fx, E prime transpose L prime, which is equal to 0, because that is it contains that. Similarly, E transpose F transpose x prime is equal to 0, and Fe transpose x prime also equal to 0. So this means that E prime transpose F, that should be, if I combine them, because that should be equal to 0, because x is not a 0, x is a non-zero column vector. So since this is 0, then E prime transpose F is 0, or even this is 0, so Fe should be also 0. So this shows that now, since F is also singular, so E is the right null vector, because E is the right operand of this matrix operation. E is a column vector, 3 cross 1 column vector. So it's a right null vector of F, whereas E prime is the left null vector of F. So from the fundamental matrix itself, if you can, we can always derive its null vectors. We will see some examples how we can do it, and those null vectors itself can give you, epipoles. Earlier epipoles are defined with respect to the projection of camera centers. So if you remember, if I give you P and P prime, then you can get those epipoles. But now even from the fundamental matrix also you can get those epipoles. So this is one interesting thing, because as we can see that fundamental matrix is inherently not dependent on any coordinate transformation of the stereo setup. So if the within the stereo setup, the relative orientations and relative placement of cameras, they remain fixed. So even if you move the whole setup in a three-dimensional coordinate space, still its fundamental matrix remains same, because those are the constraints on which, say, this imaging, say, the even if you move in a different setup, still the corresponding points, formation of epipolar plane and corresponding points and the respective lines, still they will follow the similar they will follow the same structure. So that is the reason actually fundamental matrix is an inherent property of the stereo setup. It is not dependent on any kind of global coordinate transformation of the whole setup. So if I take the whole box, this is the box, not this one. So because there are two cameras, their baseline remains in the same relative orientations or placement, and also their relative orientations become the same. So if I take this box and place it somewhere else, keeping the coordinate world coordinate with the external world coordinate system, still the fundamental matrix of this system will remain the same. So it is F, and they are only dependent on the relative orientation and the translation of the respective cameras. Since the fundamental matrix is rank deficient, that is why determinant of the fundamental matrix is 0, and F is also a projective element, because if F is multiplied by any scalar value k, still this relationship holds. So which shows that F would be F and any scaled F, they are equivalent. Since it's a element of projective space and the dimension of F is 3 cross 3, so there are 9 elements in F. There are 9 elements, but due to the scale factor, like other cases of homography, even the projection matrix, fundamental matrix also have you can express all other 8 elements in proportion to one of the other elements. Say, consider in this 3 cross 3 matrix, consider the element at the rightmost and bottommost position of the matrix, say this is your reference element, or you express all other elements in proportion to this. So that's why in this consideration here also you have 8 independent, at most 8 independent parameters. But the other constraint on F is that its determinant is 0. So this is the second constraint. So with these two constraints, actually the number of independent parameter, we will see that now in F, number of independent parameters are 7, and we call F has 7 degrees of freedom. So let us now try to understand these relationships with some example. So you consider a fundamental matrix. Say this is a fundamental matrix which has been shown, and you can see this is a 3 cross 3 fundamental matrix. And incidentally, if you take the determinant of this matrix, it will be 0. Now, if I give you 2 points 5, 8 and 7 minus 5 in the left image, compute the corresponding epipolar lines in the right image. That means I want to have 2 epipolar lines for each. So, epipolar line for each one of them. Then the idea is that compute the right epipole and also compute the left epipole. So these are the, say, 3 things which let us try to solve this. So, so this is your fundamental matrix. Now we know that the epipolar line given a point is it can be obtained by taking the product of the fundamental matrix and the point, but you have to use a homogeneous coordinate representation. So the point was 5, 6. So we have taken this for the sake of space. I have shown in as a row vector, as a row vector. It's a column vector. I have shown in this form. Actually, it means that we are multiplying the vector 5, 6, 1, and then we are getting the vector 172, 57. Incidentally, we can get also, this is also 1. It happens, it is 1. So which means that this is giving me a line. So epipolar line. So the equation of the epipolar line would be 172x plus 57y plus 1 equals 0. This is the epipolar line corresponding to 5, 6, 1. Similarly, you can get the epipolar line corresponding to 7 minus 5 points that was given as a second point. And 7 minus 5, once again you are expressing in the homogeneous coordinate system as 7 minus 5, 1, like this, 7 minus 5, 1. Then you are multiplying this with this matrix F, and you can see that you will get 80, 150 minus 370. So that you can find out. And so this is a epipolar line. So if I have the left image, say this is 5, 7, say this is 5, 6, and say this is 7 minus 5. So in the right image for 5, 6, I will have a epipolar line, say epipolar line which I have shown. Say this is the epipolar line, and for 7 minus 5, I will have another epipolar line. You know that they will be converging to the epipole. So say this is L2. So that is what it meant. So every time I am multiplying the respective coordinate by F, and I am getting this corresponding line. So this is how you can get the epipolar line. Incidentally, as you can understand that if I take the cross product of these two, L1 cross L2, I will get the right epipole. So any two epipolar lines, two distinct epipolar lines can give me the respective right epipole in this way. But we can obtain right epipole using the, as we have seen already, that using the left null vector of F, and we can obtain the left epipole using the right null vector of F. So we are coming to those computation. So next is the right epipole. As I have said that you just take the cross product of L1 and L2 and you see that big numbers because this number is big, but you can take out from here, you can take out this scale. If you take out this scale, then actually it shows this. So, which means the epipole in the image point in the non-homogeneous representation is at -1, 3. X coordinate is -1 and y coordinate is 3, and that is at the right image, in the coordinate system of the right image plane. Now, for finding out the left epipole, I could have taken some arbitrary 2 pairs of points in the right image plane and then compute their epipolar lines and respectively found the epipoles in the left plane. And from there, you have to for that you have to multiply with F transpose. As you understand, fundamental matrix with respect to the right camera, it would be F transpose. But what I will be considering here, I will be computing the right 0 of F. Now, right 0 of F means it is for our convenience, we will be converting it into the left 0. So, no, it is okay, right 0 of F. So, which means that if F is this, so F into EL, that should be equal to 0. Now, if I use this equation F, if I put this F here and EL, let me write EL as say EL1, EL2, EL3, then I get 3 equations. But since we already know that this is rank deficient matrix, we know 2 of them only, no, 1 of them is redundant. So, what I will consider, I will set EL3 equal to 1 and I will ignore the third equation. So, I will ignore the third equation. I will only consider the 2 rows to form the 2 equations, EL1, EL2, 1. So, that would give me 2 equations. So, I can express also using submatrices in a compact form. As you know that this is a 2 cross 2 submatrix, this is a 2 cross 1 column vector. So, I can write this into this plus this equal to 0, which means I will take it from the other side. So, 059 here and this inversion, almost similar to the computations what we did for computing the center of a camera in some cases I have shown earlier. So, this gives me -35 and you obtain EL1 and EL2, and since your scale factor is already 1, so this is the coordinate in the image plane in the non-homogeneous coordinate system itself. So, this is how you can compute the respective epipole in the left image. So, right 0 of F transpose also will be giving you the right epipole. We have obtained right epipole as a intersection of 2 epipolar line, but if I compute the same method using right 0, so you take the F transpose. So, you see that this is a transpose, this is a transpose operation, this is F transpose, and then in this using the same method you can obtain the right 0. So, you can see you obtain the same result what you have obtained earlier. So, this is this is also a method by which you can obtain right 0. Now, let us consider the relationships in an essential matrix. So, fundamental matrix, we have already seen that fundamental matrix, a special case of a fundamental matrix is called essential matrix, and that special case is of calibrated camera. And in a calibrated camera, if I take the respective the rotation and translation as a parameter R and T, and for a calibrated camera K and K prime, they are known. So, I can always convert this matrices such that it becomes only I0, that means only it retains this part and these relative placements of the other camera. So, within the camera centric system it has happened. That is why if I move this camera at any portion of the 3D world coordinate, still within this camera centric coordinate, still this camera centric coordinate remains valid, and your fundamental matrix also remains valid. But anyway, for the essential matrix, what we do, in this case the expression, as we know, it is you take this k inverse x and k inverse minus k prime inverse x prime. This is the canonical coordinates, and replace them into the respective essential matrix form. So, which shows that essential matrix can be expressed as k prime transpose fk. This also gives you the property of essential matrix, how essential matrix and fundamental matrix is related. Because in the same without uncalibrated coordinate system, image coordinate system, you express the usual notation of x prime transpose f x equals 0. Now this x prime is k prime xc, this is xc, and this x is k xc. So xc prime transpose k prime transpose fk xc, and this is what is the definition of essential matrix. So this is a relationship and between them. Similarly, from fundamental matrix also you can get essential matrix if you know those calibration matrices. The other representation of essential matrix using these camera parameters we have already discussed, that is T cross R. So this is once again the cross product is converted into a matrix. So we say this is T cross matrix. Let me call it T cross matrix R, and this is the essential matrix. So we can just represent it. And how many parameters you can see here itself? T is of 3 parameters, R is of 6 parameters. So there are only 6 independent parameters. Earlier we have seen that fundamental matrix has 7 independent parameters. But on the other hand, essential matrix has 6 independent parameters. Like fundamental matrix, the respective epipoles in the canonical coordinate system, they also satisfy these equations of essential matrix. Like the epipole in the left camera in the canonical coordinate system, E is C equal to 0, and the epipole in the right camera again in the canonical coordinate system of that image plane satisfies these relationships. And rank of E is also 2 in this case. We also know determinant of E is also equal to 0. So there are 6 parameters, but finally the independent number of independent parameters, because of this fact the determinant is 0, is degree of freedom is 5. So this is that puts a constant here. So that's why degree of freedom is equal to 5. Now let us consider another special case of stereo configuration, where we have only pure translation, means we do not have rotation between the cameras. That means their axes are aligned, but the camera centers, they are translated. So the projection matrices, it would look like this. You see that the rotation part is identity matrix, which gives you the which shows that there is no rotation. Now when we do this, we can write that the fundamental matrix is E prime cross K prime I K inverse. If you remember the respective relationships I have mentioned already earlier, F is E prime cross, and homography we say is homography induced by plane, and we have seen at least one homography is induced by plane, which is related with the camera parameter. So in a generic form, if there is a rotation R, then this would have been K prime R K inverse. Now this R is equal to I here, so that's why it is I. So finally this is what you get as a fundamental matrix, E prime cross matrix K prime K inverse. So this is the expression you get for a pure translation. And if the camera calibration matrices are also the same, almost these are the identical cameras, they are simply translated. So you have taken images using the same camera, for example, keeping its orientation, keeping the viewing orientation the same for the image, just translating it by T. So then you get a kind of 2 images which are the stereo images. And in that case, this fundamental matrix is replaced by simply E prime cross, because K prime and K inverse, it becomes identity matrix. So it is simply E prime cross, and which is given by these relationships. So from its epipole, right epipole, we can express the fundamental matrix in such a situation. So this is a special case of that, and we can see that the camera translation is also parallel to the x-axis in this convention, because it's a camera centric coordinate system. So it is basically the E prime is equal to 1 0 0. It is basically the intersection. It is also the vanishing point of the infinity in that line, baseline, as we have said. So it should be 1 0 0 transpose, and the F can be written as, so these values, as you can see that this is a y component, this is a z component. So these are 0. These are 0. Only this value is 1, and this value is 1, and rest are, this is 0. This is also 0. Right? This is 0. This is 0. This is 0. So this will give me this kind of fundamental matrix. So this structure is for pure translation, and there is a special relationship. So if I apply the respective the characteristics equation of the corresponding point, so x prime transpose fx. So if I apply this characteristics equation, then we can see that it gives me only the equation as y prime equal to y. So in this form, what we know that for these 2 points, their y coordinates, suppose I have, say this is a direction, say this is a y coordinate, say this y coordinates and the other point also, the y coordinates, they remain the same. And since they are axis aligned, and they form in parallel image plane. So these image planes, they are parallel. So actually, if I consider the displacement as if the displacement, if with respect to the reference plane, the displacement is displacement should be in the same horizontal line. With respect to this, the displacement will be also same horizontal, because y coordinates remain same. So it reduces your search space for the corresponding points. So we will further compute this case of pure, relate the depth information under the pure translations with that understanding. So we see once again that this is the camera, this is the projection matrices, or this is the camera matrices. From there, I can compute the camera center. As you know that camera center can be obtained by P prime itself, because this one can be written as K prime T, which means that it is minus of K prime inverse, that is the 3 cross 3 submatrix, and this is a 3 cross 1 column vector like P4. So into this column vector, and when we perform further reduction, because this is inverse of the same matrix, so it reduces to minus T. So the center here, and if I consider it is the x-axis, that means it's a pure translation, T is pure translation. So the center C prime is denoted like this, minus Tx 0. See, you should note that though I am saying it is right, but mathematically actually it is in the negative direction. So that is how you have obtained here, which means that to keep it right, say if I put it minus, or if this T is minus Tx, then this should be plus. So when Tx is positive, then it should be negative. So this is a relationship we understand. It's a mathematical abstraction, and the point as the negative and positive, it depends upon the mathematical convention that you are using or the values you are using. Now let us continue once again. So the case is that first let me consider that how to get the x, the homogeneous representation of this point which is given say x, y, z, and we know that in the non-homogeneous representation I can write it as x, y, z 1. Now when I am writing the corresponding x in the canonical coordinate system, if I use k inverse x, then I know that then it becomes in the canonical configuration, like an calibrated, since we know the camera calibration, then this is placed at a distance 1. When k inverse x means this image point is placed at a distance 1 and at a depth 1, basically in the x z direction it is placed at its z value is 1. So if I represent it, its z value should be equal to 1 for k inverse x. So finally the x tilde can be then represented by z into k inverse x. If I multiply z with the z with this in this direction, if I multiply that depth value, then actually I will get the respective coordinate. So that is a relationship between the scene point and the image coordinate for a point at a distance z. That is a three-dimensional coordinate relationships with respect to this particular using this camera matrix. With respect to the other camera system, if I express its coordinate, now since it is translated by t, so we understand that x prime plus t, that is the with reference to this coordinate system, the respective coordinate would be x prime plus t. Now that is the translation. Okay, that is the translation, x prime plus t, and that should be also would be expressed in its own image coordinate, because this is the calibration, this is the normalized or canonical coordinate. Again, by multiplying with z, we get because there is no other thing has been changed. Your orientation, there is no orientation, so z axis remains still parallel. So if I multiply with z into this, you will get the three-dimensional coordinate with this coordinate system, with respect to the coordinate system for this camera. So if I consider say k equal to k prime, so what I would do that I will take the x prime minus x equal to x prime plus t minus x prime, and that would give me, if I take the difference of this, that would give me the x prime equal to x plus kt into z. So this is a relationship. This is how the two points with corresponding points, they are related with this particular special case. Now k is the calibration matrix, camera calibration matrix, and t is the respective translation parameter of the projection matrix. Now if k is considered as in a simpler form, that means only diagonal matrix, and say the image planes are placed at a focal length f. So this expression becomes this f dx x prime minus x, and so this is a very familiar expression. This is called actually the parallax. That means the shift of the image point in the right image plane, the amount of shift along the x coordinate, x direction, that is the parallax, and the inverse of that, or we call it disparity. So this is called also disparity. So z is, as you can see, proportional to the inverse of this disparity, but we can exactly compute by using the focal length and also the translation of the origin or center of the camera along the x-axis in that case. Then you can exactly get the respective z value. Now, this is what can be used for computing depth of a three-dimensional point in a particular stereo setup using this kind of constraint configuration of a stereo setup. Now, let us apply this method for a general motion of a camera. General motion of a camera means earlier we have only considered translatory motions, but let us consider also rotation, which gives the general scenario. So, you have the reference camera. Once again, it is given in this form, semi-canonical form. That means you have the calibration matrix. It denotes the uncalibrated camera where the center is at the origin, and the other camera is given also in a very generic form, where you have the respective parameters, rotation and translation, and the calibration matrix. So, to make this now apply the previous theory, what we can do, we can apply the homography between these two scenes. First, what we will do, we will consider that say you have an image, and its say corresponding image point is here. So, first we will be finding out what is the if I apply a rotation homography. So, we rotate it in such a way that these two planes, they become parallel, which means their orientation, with their relative orientation, become identity matrix. There is no orientation about their axis. Only we have the translation. So, which can be done by performing rotation by centering when your center of rotation is passing through this camera center, and your center of rotation is along say y axis here, center of rotation. So, that you can rotate in such a way that they become parallel. So, their z axis get aligned. Okay. So, you are rotating, so their z axis gets aligned. Now, this so you have to apply some rotation so that their z axis get aligned, and for that there is a rotational homography we have seen, and this rotational homography can be expressed in the form of k prime r k inverse. You keep the other parameters same, so you get equivalently this is the projection matrix. So, and then applying homography, x is mapped to this point, and then the corresponding point at this point, that means that this correspondence is now established between this point and this point. So, they form a equivalent stereo setup, and which satisfies also that constant, there is no rotation, only there is a translation t, the previous case, because they have the same rotation with respect to this one. So, with reference to these two cameras, they do not have any rotation among them. So, their rotation matrix is identity. So, with reference to this, and note that the center of this camera is at origin. So, it satisfies the other property, case of stereo configuration. So, now this x prime and this point is related by the same relationships, and now I also apply this homography, applying the relationship with the homography, I can relate x prime with x, that means this point. So, this is finally can give you also the relationships between two corresponding points under a general framework, and it relates with the depth information that we see here. So, this is a parallel stereo, and it once again it shows that how this homography could be k prime r k inverse. It follows a similar logic what we considered for the case of plane induced homography, but here it is easier to see that X2 is also an say image. X2 is also an image of the scene with this camera matrix. So it is K prime R0X, because they are that is how the homography is established. They are the image of the same scene point. So after reduction you get K prime RI0, and then you introduce this particular algebraic manipulation. You multiply this K inverse and this is K. Effectively it means you are multiplying with an identity matrix which remains the same. So you get K prime R K inverse, this part, and this part, which again it shows this is the projection matrix P, this is P. So P into X gives you X. So this is how X2 and X is related, and this is the homography what has been shown here. So this is a case of the general camera motion what we discussed. Now let us once again understand this particular type of relationships with an example. You consider a stereo setup with two camera matrices P and P prime which are given here. So you can see here in this setup the respective 3x3 matrix, they remains the same. So I can make this matrix as K, and if I take it out, this part would be I and this part would be also I, and this is 0, but this will be considered as, say, this is, if I take it out, of course, you know that while taking out you have to consider that K into, so suppose this will be converted to T, but K into T should be equal to this matrix, which means actually it would be 10 by 6, 0, 0. If I multiply this with this, T equal to 10 by 6, 0, 0. If I multiply K with this T, then you will get particular column vector. We will see that thing. So anyway, so if I give you these two matrices where there is no rotation but there is only translation in the stereo setup, and if I give you two image points 6.8 and 9.338 in left and right cameras, compute the depth, that same formulation what we have done earlier. So this is the case as I was telling you. So which means K should be equal to this in this case, and T is 10 by 6, 0, 0. And if I apply X prime equal to X plus KT by Z. So Z is given by 6 into 10 by 6 divided by X prime minus X, which are given you. That corresponding points are 9.33 and 6 for the X prime. Y prime is already same. If you check the problem notification, say Y coordinates, they remain the same. They satisfy that constraint of the epipolar constraint of the characteristic equations. So you get this Z equal to 3 solving this problem. Let us consider the case of estimation of fundamental matrix. Now, while when you are considering this estimation, we know that the observations what you get from two images, from those two images we can identify the pairs of corresponding points by doing different image processing we have discussed already, say feature extraction, and by matching the features you can get those corresponding pairs of points. So given those images from the stereo setup, you get them. So each corresponding pair will give you one equation, but this is only one equation. I have already mentioned in my previous lecture why it is, how you can check that this is one equation, because if you check the matrix dimensions of this matrix multiplications, you will find this composite matrix multiplication finally reduces into 1 cross 1, which means this 0 is also only a scalar element. So this expression is a linear expression in terms of the elements of F, and what is known to you x prime and x is known. So my unknown would be f, and each one will give me an equation. So I can write it in this form, this equation. As you can see that if I get the pointers x prime, y prime 1, and the other point is x, y 1, these two image point, and then they take the transpose f and multiply. So that would give me this equation. Use this representation. It will, so you see it's a linear equation, all in terms of unknown outcome. These are the unknowns. And you can express this in this form. So this is the, row vector, and this is the column vector. And naturally this one is of dimension 9 cross 1. So one equation, one corresponding pair is giving me one equation. Now you consider there are n points. For each point you get another row. So if I consider a matrix, so for the first point I will get the first row, and this is my unknowns, f11, f12, 2, f33, say, which is 9 cross 1. So first row into this column will give me 0. So let me set these equations. So first row will be 0. Second row again multiplied this will give me 0. And it goes like this. It goes like this. Similarly, the last row will also give me 0. So this is basically, this side will be 0. And since there are n, corresponding pairs, there would be n row. And since there are 9 unknowns here in these equations, there would be n cross 9. So the dimension of this matrix is n cross 9. This is of 9 cross 1, and this should be of n cross 1. So this gives you a set of linear equations, n linear equations. I can write in this form. As you can see that the whole thing for the n observations corresponding pairs of corresponding points, I will write in this equation. So again it will give you a set of linear homogeneous equations, because this side is 0. And the way we have solved these conditions, that we can obtain f by minimizing this norm, AF. By minimizing this norm, we can obtain f so such that, the f is equal to 1. That is one constraint. But the other thing is also there, earlier it was not there, the determinant of f should be equal to 0. So by solving them, you may not get f, you can compute an f, but by solving them, you may get, non-singular f. So for that, what we can do, so let us see. So that is one problem. So you can get a solution up to scale, and then there are, it's minimum 8-point correspondences, because you can always, like before, you can always express all other elements, say with respect to this f33, and solve it. So this is the minimum 8-point correspondences, but still you are not ensuring f is, determinant of f is 0. And so for 7-point correspondences from linear combination of smallest and second smallest eigenvectors. So we will see later on, actually, when we consider the, if I use only 7-point correspondence, because there is another constraint, determinant is 0. So actually 7-point correspondences are sufficient to get f. So there would be singular values. There would be 2 singular vector values, and from there, if I have to find out the respective solutions. So let us not discuss that. Let us consider this particular problem of estimation of fundamental matrix using the 8-point minimum 8-point or using this method. And one of the problem, once again, as you can see, that these values would be very high, because these are the coordinates. Product of these coordinates will be further, it accentuated this problem further in this case. So you need to have normalization of the data, and we apply the same normalization method. So by transforming the image to a coordinate system with -1 1 -1 1, so that you place the coordinate at the origin, and this is say -1 -1, this is say 1 1, and in this way you can get a coordinate transformations like this, and this you can show that this is how you can do this coordinate transformation. And after that you can apply this least square method, and which is shown to be given good results. For taking care of singularity, as I mentioned, that since the rank of f is 2, and what we can do, we can perform the singular value decomposition of f, what is obtained, estimated from your least square error method. So you can order these singular values, sigma 1, sigma 2, sigma 3. As you know that for singular value decompositions, you get these matrices which are both 3 cross 3 matrices, and considering its rows and its columns, they can be decomposed into 3 matrices, and whose superposition would give you the same thing. Now you just ignore this part by setting it to 0, which is the smallest singular value. Then the effect is minimum. So this is your finally the result of this estimation from f. You perform the correction, this correction, to make it singular. Otherwise this f is not singular. If I take the determinant of f, it is not 0, but as you know that fundamental matrix determinant has to be 0. So this one has to be considered. So that is what you have to use the singular value decompositions, and the compute closest rank to approximation. It just shows that if your estimation, if you don't use non-singular f, that means you stop at in the very first stage. After that, you don't perform those corrections using singular value decompositions, you will find your epipolar lines, they are not converging. That is the problem. But when it is singular, then epipoles are very well defined, precise. That's the singularity of the epipole, because that at epipole you cannot form epipolar line. So when it is singular, it would be all of them are converging. This is a very interesting result, has been shown from this particular book of Hartley and Gisserman. So with this, let me stop here today, and we will continue this discussion in the next lecture. Thank you very much for your listening and patience.